Okay, for those of you that are watching this at home, which I know everybody that's at home is definitely watching this, we spent the first 5 minutes, well, 20 minutes, really 15, so 5 minutes worth of pledge and stuff, working this problem, okay? So you guys at home probably ought to pause the video right now, spend 15 minutes, and try to see if you can do this, because this is going to be a problem that's going to be similar to what's going to be on the quest on Monday. Okay, now you only have one of them, but because they take 15 minutes to do. But everybody needs to know how to do this, so this is a good practice on how to do that. So don't just wait for me to just go over it, which I'm about to do. Pause the video, work it, find out if you know how to do it, and figure out where you're getting lost at, what you need. And if you need, send me an email, we'll try and figure it out, you know, or we can Google me. All right, so we have the balanced equation. First things first in our balanced equation, we need to determine which one is the precipitate over here. What are our big three solubility rules? All nitrates, all alkaline metals, and all ammonium, which is the NH4+, the second one from the top on the left, okay? If it's got any of those three ions, then it's always going to be soluble, meaning aqueous. This is an alkaline metal, potassium, group 1A. Nitrate, so this is doubly soluble, soluble for two reasons, okay? So that's going to be aqueous. Well, if this is aqueous, that means this one has to be the solid. If they're all aqueous, then it's going to be no reaction at all. They're all just kind of spectator ions. They're all floating around doing nothing. You got to have a solid, liquid, or a gas form. All ionic compounds are going to be solids because they have high melting and boiling points. Okay, so if it's a metal something, it's going to be a solid. Okay, you're not going to get liquid or a gas from an ionic compound. All right, so that's first thing. Next, what do we have to find? The limiting reactant. We do that by taking the given to moles for each one. Now this one's given as milliliters and molarity, so we're going to go 0.0250 liters of Ki times 0.5 moles per liter. So that's going to tell me, and so it's going to be 0.0125 moles of Ki. But what do I do with it? Divide by 2, and that comes out to 0.00625. Yeah, okay. So now this number's nothing. This is how many moles I have. That's the more important number, but we're just going for the right ratio. Now we're given grams of this one. Well, what's the conversion factor between grams and moles? The molar mass. So we're going to say 5 grams PbNO3 2 times 1 mole over 331.8. 331.2, close enough. Okay? And then that turns out to equal how much? 0.0151 moles of PbNO3 2. Now we don't need this divided by 1, there's no need to actually show that and whatever. So we know that it's this compared to that. Obviously this one's much smaller than this one. So this is my limiting reactant. Okay? We're all good to that point. Now we need to calculate the concentrations of each thing that's remaining. Now, since this is the limiting reactant, how much Ki remains at the end of the solution? 0. Since this is a solid, how is this going to contribute to ions in solution? It doesn't, because solids sit at the bottom. They don't break apart. They're not dissolved. So we're going to get 0 from this. So the only thing that's going to be in solution, when we look at our beaker, if we look at the beaker, okay, we've put in the 25 milliliters of Ki, and we know, and then we put in the 5 grams PbNO3, 2. Okay, so now it all mixes and reacts. What's going to be at the bottom? The PbI2. That's all just going to be sitting on the bottom as a solid, as a precipitate. Now, all of the potassium goes to potassium nitrate. So we're going to have some K plus ions floating around, and we're going to have some NO3 minus, because ionic compounds are going to dissociate. Okay? Now, we're also going to have some excess lead nitrate. This is my excess reactant. So I'm going to have some Pb and some more NO3 2 minus. Okay? So I'm just going to put some more Pb 2 plus up in there. So I got to know those 3 ion concentrations. Is that making sense as far as just understanding what's going on? So we have, this is sitting at the bottom. This is just floating around, broken apart as the ions, K plus and NO3. And then some of this reacted, but some of it's left over, and the part that's left over is still going to be Pb 2 plus ions and NO3 2 minus ions. Okay? Now, here's kind of the shortcut. If it's aqueous here and aqueous there, that means it didn't change at all. So however many moles of potassium I have here, that's how many moles of potassium are going to be over there. The same thing is true with nitrates. The nitrate is aqueous here, it's aqueous there. So really the nitrates just, once they got into the solution, nothing happened. They just stayed there. They just floated around. So however many we started with, that's how many are still there. Because none of them precipitated out. Okay? So once we know that whatever's aqueous here, these 2 ions are going to be the same as what we started with. Because nothing changed, nothing precipitated out, nothing, left the solution. The law of conservation of mass is atoms are neither created nor destroyed, they just rearrange. So these are just spectator ions in our reactions, and so I know that Ki, I have 0.0125 moles of Ki. So how many moles of K am I going to get from that?
0.01.
The same amount, because it's 1 to 1, because it's 1 K and 1 I for every molecule. Okay? So I know my K plus concentration. Emmy, can you see, am I still on the screen over here?
Yeah.
Okay. K plus is equal to 0.0125 moles divided by the volume. Now, some of the questions, and they asked this in the other class too. When you add a solid to a liquid, right? So a solid, 5 grams is added to the 25 milliliters, we assume that the volume's not going to change. Okay? That we're still going to assume the volume of the whole thing is just 25 milliliters. We did that on the one, I think number 88, where we put the 15 grams into 55 milliliters, and you just assume that again it stays at 55 milliliters. Okay? Technically, the solid does increase the volume slightly sometimes, but generally we don't figure that in because that gets too complicated. All right, so we're just going to say 0.0250 liters. So that turns out to equal 0.5 exactly. All right, 0.500 molarity. Now we do the same thing with the nitrate. However, in this case, for every 1 mole of lead nitrate that we have, we know that we have 0.0151 moles of lead nitrate. How many moles of nitrate am I going to get in solution? 2 times that, right? 2 times that. So I'm going to have, it's going to equal 2 times 0.0151 moles divided by, does everybody understand that too? Because when lead nitrate dissolves in water, it dissociates into a Pb2 plus and 2 NO3 minuses. Okay? Now, if you wanted to do it a different way, we could figure out how many moles of KNO3 got produced. Well, I know that this is my limiting reactant, so 2 makes 2, okay? So therefore, I know that I have the 0.0125, so I should have, does that come out the same? Yeah, but 2 makes 2, so I have this many moles, it should make the same number of moles of KNO3. So however many I start with should come out to the same. Is it not? Oh, I know my mistake.
0.0125 again.
Oh, yeah, okay. Did all the lead nitrate react?
No.
No. Okay? So you can't just say, you know, this many moles here. Backtrack, gotta clear my brain. All right, so this is how many moles of lead nitrate that I have, but not all of it react, not all of it goes to here, okay? So I can't say that it's gonna be 2 times the 0.0151 because not all of it reacted. I need to use the amount that reacted. The amount that reacted is going to be twice, half of the moles that we have here. So it's really going to be the 0.0625 actually reacted. Okay? Then we got to multiply that by 2. That's not right. I'm still wrong. Come on, Steve. I'm doing the lead now. Okay. We're going to backtrack. I wish I could rewind on the video so I don't have to prove that I screwed this up. Okay? When we're looking at the nitrate, once again, this, however much nitrate we put in is how much nitrate, I was right in the first place, just for the record. However much nitrate that I put in, that's how much nitrate we're gonna have. Some of it's gonna be in this form, some of it's still gonna be in this form. But it's still all gonna be in the solution. The nitrate's just floating around not doing anything. So I know that I put in 0.015, so the nitrate is gonna be 2 times 0.0151 moles. Okay? So that's gonna give me how many moles of nitrate divided by the 0.0250. I don't know why I doubt myself, but sometimes I do. So what does that turn out to be? 1.21 molar. I hate it when I mess up like that because then it just makes y'all confused, and I'm trying to unconfuse you and not confuse you more. So once again, all the nitrate that I put in here is still going to be, if it's aqueous here, it's aqueous here. Whatever you start with, whether it's limiting or excess, whatever you start with, that's what you're going to finish with, because they're not just going to disappear. All right, so now, the one that's trickier is the lead, because some of the lead precipitate out of solution, so we don't have 0.0151 moles of lead nitrate anymore, or 0.0151 moles of lead in the solution anymore. Some of it precipitated out. So we have to figure out how much precipitated out. So, for the lead, okay, we're gonna go and say, all right, well, I know that I have 0.0125 moles of Ki reacted. That's how much I put in, that was my limiting reactant. For every 2 of these, only 1 lead nitrate reacted, so it's 1 mole PbNO3, 2 for every 2 moles Ki. That's going to tell me how many moles of lead nitrate, and for every mole of lead nitrate, how many leads do I have? Just 1, so that's just going to tell me then, so we're 1 over 1, so divide that by 2, that's going to be the 0.00625 moles of Pb2 plus used. How much did we start with? Well, we started with 0.0151. So the amount that's excess is equal to 0.0151 moles minus 0.00625 moles. And that turns out to equal 0.00885. Is that what, 0.00885? I bet this is not on the camera anymore, so just move it just a hair. All right, so that's how many moles of lead are still in the solution. So I still need to do them. I'm just going to go up to here then. What's the lead concentration going to be? How do I find the lead concentration?
Excess divided by the.
Well, I just did that.
Yeah.
So now that I have moles
Divided by the volume.
divided by the volume, the 25 milliliters again, changed to liters. So it's going to be equal my 0.0085 moles of PV. That's how much is left in the solution. And that turns out to equal 0.354. All right, so now, in a nutshell, well, let me let you finish copying all that down, then we'll nutshell it. Did we get that right? Did we get it all the way through? No?
I messed up
Okay.
on nitrate.
Amy, did you forget the 2?
I used the limiting reactant instead of the.
I gotcha. Okay. And we're still copying. So, again, if you stepwise, what do I do? You figure out how many moles of each thing are present. You figure out which one's your limiting reactant. Okay? You're gonna have 0 of that one. The only thing that's going to be a problem is in the solid, which one actually is precipitating out. That's the one where the ion concentration is going to change. If it's aqueous on the left and aqueous on the right, so the potassium is aqueous here, potassium is aqueous there. Therefore, the potassium is going to be the same as whatever we put in, 0.0125, 0.0125. Okay? Same thing on the nitrate. Nitrate is aqueous here, it's aqueous there, which means it didn't change at all. So I know that I have this many moles of lead nitrate. Now this is where you have to understand the dissociation. Since there's 2 of them, I'm going to get twice the concentration. For every mole of lead nitrate, I'm going to get 2 times that for NO3 minus ions, divided by the total volume. And then lastly, for the lead is here, some of that precipitated out. Okay? There's no iodide left because it was limiting reactant, so we know it's all gone. So, but the lead is excess. So I have nitrate that's, really the nitrate's just floating around, but you know, it's the same. The lead though decreased. So we have to figure out how much did it decrease by. So I know how much I started with. But I just do simple stoichiometry, a mole-to-mole ratio. I know how many moles of Ki, my limiting reactant. For every 1 mole, 2 moles of Ki, 1 mole of lead nitrate reacted. So this is how many moles got used of the lead nitrate. Which means we subtract, that's how many moles excess that we have. So the only difference on the solid, you have to figure out the metal, how much got used using just the mole ratio. subtract that, and that's gonna give you the moles left over. We good with that? Do we need to do one more? Or you just tired of them? Somebody talk.
It's a quick way to pass 20 minutes.
Quick way to pass 20 minutes, well, the whole class period actually now. And so 20 minutes to do it and 20 minutes to go over it. Can you do one on your own? The whole point is, can you do one on your own?
Let's do it.
Yeah. It's
All right.
worth the 20 minutes.
Well, hopefully, now that you're getting, hopefully have a little bit of idea how to be better. Now, the other redeeming thing about this is that, again, the quest is gonna be Monday. You guys are gonna be at home. The other kids are gonna be here. As much as I trust everybody implicitly, there are probabilities that some would be using a notebook as they're taking this quiz, okay? That's just the nature of the beast. Therefore, to make it fair for all, including those that have to take it in class, it will be an open note quest. So at least you have some guideline, you know, to kind of go back and say, okay, well, what did I do here and what did I do there, okay? So it's more of a graded worksheet than a quiz, because I can't ever give a real quiz virtually. I mean, because there's just no way for me to monitor and guarantee that, you know, and so I don't want to penalize the kids. Oh man, everybody's home cheating, I have to be in school. You know, then we get all kinds of phone calls and. So that's the only way I know to be fair, but it doesn't always give me a true indication of how well you're understanding everything. All right. Am I here?
No. Yeah, that's good.
All right, so, let's say 15 grams of AgNO3 are added to 50 milliliters of okay, I gotta do some quick math here in my head. 15 K2CrO4, 64 to 52, it's 116, 70, 184. 50 milliliters of a 0.5 molar K2CrO4 solution. What are all the concentrations of the ions in the solution? Now, those of you at home watching, again, try to do this. I'm gonna stop the video and then I'll restart and make a part 2